Okay, so before our break, we have learned about the general ideas for the functional principle component analysis. And we know that the FPCA is an important tool for dimension reduction. It projects an infinite dimensional function to finite number of LPC scores. And we also have learned the interpretations for the LPCs. Okay, so now let's we continue. Let's look at some mathematical details behind the LPCAs. So basically here, it's very close to PCA. So for the PCA, we mainly focus on the covariant function capital sigma, right? So we do the Eigen decompression for the covariant function sigma. We get the eigenvectors ui, and we get the eigenvalues di. So for FPCA, we will working on the functional covariant function. So when we have a one-dimensional curve xt, we can estimate the covariant function will be a bivariate function sigma st. So what we will do is we can do the KL decomposition for the covariant function sigma st. We are written as a linear summation of dj times wjs times wjt. So wjt will be the eigenfunctions for the covariant function sigma st. dj will be the eigenvalues. So the LPC score Sij will be calculated as the weighted as the inner product between xit and the LPC wjt. And the variance of the LPC score will be equal to the eigenvalues dj. So here dj represent the amount of variations in the direction wjt. So therefore, we will look at the ratio dj over the summation of the dj as the proportion of variance is planned. Okay, so generally, for when we do the Eigen decompositions, only the top few dj's will dominate the whole summation. So when we see this summation go to infinity, we actually don't have to actually go to infinity. So if you calculate like, for example, the top 10 eigenvalues, probably it will be close to all the eigenvalues summed together. Okay, so this is a kind of the connections between PCA and FPCA. Okay. So basically, in the end, they all connect to the Eigen decomposition problems for the covariance matrix or the covariant function. Okay, so so how we do calculate the LPCAs? Okay, so basically, we will solve the Eigen equation problem. So we know that the WIT, the LPC, is the eigenfunctions of the covariant function capital sigma st. So this will be the eigen equations for sigma st. So how do we solve these eigen equations? So there's two options. So the first option is that we can first define a fine grid for the time. So T1 to Tk. So this fine grid does not have to be the real time points with observations. So it can be arbitrary fine grid. And then we can evaluate this covariant function sigma st at this grid, and we get the matrix, covariance matrix capital sigma. And then we will do the Eigen decomposition for capital sigma, then we will get the eigenvector for capital sigma. Okay, So this is the first option we can do. Okay. So the second option we can do is that we can do the this is also how we used in the FDA package. So basically, when we for the curve XIT, it is already written as a linear combination of basic functions. So what we will do is that we will write down the eigenfunctions WIT as a linear combination of the basic functions, and then we will plug into this formula, and we will find out the eigenequations in terms of the basic coefficients. Okay. So let me show you how this second option works mathematically. Okay, so basically we have this n curve x1t to xnt, right? And so we will this n curve will be written as a linear combination of these basic functions phi1t to phi jt. Okay, so then all the basic coefficients will be written as a coefficient matrix capital C. So this coefficient matrix capital C, each row will be the vector of the basic coefficient for one curve. Okay, so this is C will be a n by j matrix. Okay, so then the sample covariance function sigma st will be written as an average of the xit multiplied by xrs. So then we plug in the formula for the xt. It can be written as this quadratic form. Okay. So then we will express the FPC W2T as a linear combination of the basic functions phi1t to phi jt. This is the vector form. B is the basic coefficient. Okay, so here we want to maximize we want to solve this current function subject to the constraints that the length of the LPC will be equal to 1. So you can see here the integral of the square of the WT can be written as the B transpose times this integral times B equal to 1. So this integral only involved, we call it W, capital W here, only involved the basic functions, right? So all these basic functions can be evaluated numerically. And so this integral, this matrix W, actually is pretty easy to calculate. I will show you later how we do it. So this is the capital W. So after we got this, so then we can plug in the expression of W2T and the linear combination of the basic functions to the eigenequations. So this is the formula for the current function sigma st, and this is the formula for W2T, right? And we can plug in this. And after we plug in this, we will notice that because this is the integral with back to t, so phi s will be a constant with back to t. And we can take all the constant outside the integral. The basic coefficient C transpose times C is also constant with back to t. So we can take this outer integral as well. And the coefficient to the for the LPC D will be also constant. So we can take outside, but we have to keep the order. Okay. So you can see here inside this integral only will be only involve the basic function phi t. So will be the matrix W here, right? Okay, so now we are able to write down, simplify these eigenfunctions, and because these eigenfunctions is true for phi s at any time s, so then you can think about this term will be the coefficient to the phi s, and this term rho b will be the coefficient to phi s as well on the right side. So if this function is equal to each other, which means that the coefficient had to be equal to each other, right? So then we can drop the phi s, and we will have this formula equation. Only involved the b here, and we know that this C is a basis matrix, can be calculated already, right? And the W will be the is also only involved the basis functions, can be calculated as well. So we know C, we know W, and we also know the constraints is written as this quadratic form, B transpose W times B equal to 1. So to do this, we will first substitute U equal to W 1/2 times B. Okay, so then we can written multiply the both sides of the equation by W 1/2. So multiply W 1/2 on the left side, and we also multiply by W 1/2 on the left side, on left side of the equation. Okay, so then we can write down this W 1/2 times B as the U, right? So this will be replaced by the U, and this part will be replaced by U as well, right? The reason we do the substitution is that these constraints, B transpose W B equal to 1, will become U transpose times U equal to 1. So we don't have the W between, okay? So now we can see that basically the U is an eigenvector of the matrix here, right? This will be the standard eigenequations. So C is known, W can be calculated, so we can calculate this matrix right away, right? And then we can find the eigenvector of this matrix. So we will have this U here, and we will get the U. After getting the U, we can get the B. B will be the coefficient to the for the FPCs, right? So after we know B, we can get the WT. So this is how we get the FPCs. Okay, so let's kind of show you how we do it. Okay. So any questions about how we derive the LPCs? Okay. So let's continue. So let's look at one example. So this is the delay temperature, is delay average temperature recorded at 35 Canadian cities. Okay, so here each curve represent the delay temperature over 1 year for one city. Okay, so here we want to find the variations among these curves. We do the LPCs. Okay, So this is the LPC we will get. So here we plot the top 4 LPCs. Okay, so you can see here when we look at these LPCs, it has a lot of wiggle things, wiggle trend. So in that part, it will make us difficult to see the trend, major trend, and also to interpret the LPCs. So what we will do is that we will smooth out these LPCs. Okay, so we will not like first get these LPCs and then do the smoothing. So we will doing the smoothing, control the LPCs during the process of the LPCs. So how do we do it? So basically, here for the regular LPCs, we just learned that the first LPC will maximize the variations of LPC scores, right? So here I write the LPC score as Fi. And so because the length of the WT equal to 1, so we can written as this summation as this summation divided by the length of WT, because this length is equal to 1, so it's the same, right? Yes. So how we adding the smooth control on the LPCs? So what we do is that we will adding a integral of the second derivative of the WT square as the roughness penalty, and lambda is the smoothing parameter. Okay, so we will constrain that the length of WT plus the lambda times the second derivative of WT equal to 1. So you can imagine that if WT is too wiggly, then if too rough, then the second derivative of WT will be very large. So then it will be impossible to have this integral equal to 1, right? So this is kind of control how the WT cannot have to be smooth enough, right? Yeah, so this is how we control the smooth LPCA. So this is the results after we adding this smooth control. And so you can see, I will explain the interpretation on these LPCs later. So here, I also want to mention an alternative definition for the roughness. So in my previous slides, I defined the roughness of a function f by looking at the second derivative of the function, right? So here, capital D represents the derivative of t with back to dt. So I don't write down the dt part just to make it simple to write. So this is one way to define the roughness penalty. So the reason we're using the second derivative to define the roughness penalty is because we think that the linear function f, if f is a linear function, it is the most smooth we can think about. It should get any roughness penalty. So the linear function will get a 0 roughness penalty. So the second derivative of the linear function will be equal to 0, right? You have no roughness penalty. Okay, so so for weather data, this ft is a periodic function, right? So for periodic function, for the most smooth periodic function can you think of? What's the most smooth periodic function you can think of? I will leave for 30 minutes for you to think about what's the most smooth periodic function you can think of. Can you give some thought and let me know if you, please tell me if you know the answer. Okay, it's 30 minutes. Any answer? The most smooth periodic function? Okay, so the most smooth periodic function will be sine cosine function, right? So you can think about the sine cosine function is very smooth. I will not think about the sine cosine function to have any roughness, right? So therefore, I want my sine cosine function get a 0 penalty. So I want to define the operator. If this operator L defined on the sine cosine function, it should be equal to 0. Okay, so therefore, to get this, we will define an operator called a harmonic acceleration operator, defined in this way. Okay, so it's omega squared times the df times the d third derivative of f. So here omega is equal to 2 pi over p. P is the periodic of the function. So so if we define the harmonic acceleration function, then the sine cosine function will not get any roughness penalty. So then we will using this harmonic acceleration operator to define our roughness penalty term. So we instead using the second derivative here inside the derivative, we will using capital L inside the derivative. Okay, so so this actually harmonic acceleration operator is very popular when we define the period to estimate the periodic functions. Okay, so so almost in most cases, when we want to estimate periodic function, we will using this harmonic acceleration function operator to define roughness penalty. Okay, so this is another roughness penalty definition. Okay, so now let's look at the go back to the how do we interpret the LPCs. So here, this black curve is the first LPC. You can see here, it is positive over the whole year, right? So with the highest weight in the winter and lower weight in the summer, right? So if you look at the temperature functions, you will see that for these 35 curves, it has the lowest variations in the summer and wide variations in the winter. So that's why for the first LPC, it is able to automatically choose the highest weight in the winter and lowest weight in the summer, such that the weighted average will have the largest variations, right? So if you understand, if you have been know Canada weather, you know that so Canada actually it's a very big country, and so in the in a city like Toronto or Montreal, it's kind of has the continental weather, so it's very cold in the winter and hot in the summer, and so for the city like Vancouver, it's close to Pacific Ocean, and it's actually the winter is very warm. So you can see probably this curve is Vancouver. It will be every temperature will be above zero in the winter. So so therefore in Canada, the winter, the cities have the largest variations, but in the summer they are all pretty warm. Yes. Okay, so that's why the winter get the largest variation, largest weight. Okay, so this is the first FPC. It's standing for the average temperature over the whole year with the highest weight in the winter. So the red curve is the second LPC. So you can see that the second LPC is negative in the summer and positive in the winter. So you can think about the second LPC score as the change of the temperature between winter and summer, right? And the green lines is the third LPCs. You can see that it is positive in the fall and negative, sorry, positive in the spring and negative in the fall. So in that case, you can interpret the second LPC scores as the contrast of temperature between fall and spring. And for the third LPC, fourth LPC is the blue curve. It is positive in the winter, negative in the spring, and positive in the summer, and negative in the winter. So, sorry, negative in the fall. So you can think about the fourth LPC as the contrast between summer, winter, and spring, fall. Okay, so this is how do we interpret the 4 LPCs. Okay, so really we want to look at the sign of the LPCs, where it crosses zeros. So therefore, when you plot the curve, I recommend you to plot the horizontal curve go through the zeros, just to see where the LPC is positive, where the LPC is negative. Okay, so this is how we interpreted the LPCs. Any questions? Okay, so so now let's calculate how many or decide how many LPC we need for the LPCA. So typically what we do is that we will do the Eigen decompression, right? We find the eigenvalues, dj. We know that dj represents the variance of the LPC scores. So then we can look at the ratio of dj over the whole summation of the eigenvalues, and the proportion of the variance is planned by each components. So then we will look at the cumulative variance is planned by the top LPCs. So you can see that the first LPC is planned around 80%, after adding the second LPC, it will explain over 97%. After adding third LPCs, it will explain 99%. So then we will see that, if we want to explain over 99% of the variations in the data, or explain capture the 99% of the information from the data, we will choose the 3 components, right? So if you want to capture 95% of the information in the data, we will choose the top 2 LPCs, okay? So you can see it's a very, we only choose a very small number of LPCs. Okay, so another very important plot when we do LPCA is that we want to plot the first 2 LPC scores for each observations. Okay, so here, this is the graph. Basically, the x-axis is the first LPC score. The second LPC x-axis is the the y-axis is the second LPC scores. So then basically we project the 35 curve to this 2-dimensional space, right? So then we can see how this data looks like. And so the first LPC standing for the overall temperature. And so you can see here, like cities like Vancouver or Victoria has a very large first LPCs because it had a warm weather. And like a Resolute actually is in close to Arctic Ocean, so it's very cold. So it had a very low LPC scores. And for the second LPC, it stands for the contrast between summer and winter. So for Victoria and Vancouver, it has like a warm winter and cool summer, so they get a pretty big second LPCs. And for the city like Winnipeg, it get a very cold winter and a very hot summer. So therefore, Winnipeg get the very negative lowest second LPC scores. Okay, so this is how we look at the LPC scores. You can see that after we project the from 30-50 curves to this 2-dimensional space, it is very easy to do the clustering on the cities, right? So this is a very classic way if we want to do the clustering analysis on the functional data. Okay. Another very important feature for LPCA is that we actually can predict the missing data, even the missing data happening at a big period. So this is kind of show you one examples. So you can see here, these red circles represent the observed temperature in Montreal for the first 120 days. Okay, suppose we have the data for the temperature after 120 days is completely missing. So in other words, all these red circles, sorry, blue circles cannot be observed, are missing. So what we can do is that we can using FPCA to predict the whole curve after 120 days. And you can see that the prediction actually is very accurate, even we don't know this area completely, okay? So this is a very powerful feature for LPCA. It is able to estimate the missing data for a long period. So how do we do this? Okay, so we will using the conditional expectation. So basically, suppose we have xt only measured partially. So sorry, this should be xt, and we only observed xt on a few time points. So what we will do is that we will first estimate W1T and WJT from the fully observed data. And then after we get these LPCs, W1T to WJT, then we will fit the LPC to the observed data ZT here, and we will do a least squares. We will minimize the distance of the observed ZT with back to the linear combination of the LPCs. And we will, this LPC score Sj will serve as the unknown coefficients. So we can do the least squares estimation, and we can estimate the LPC score Sj. So after we get the Sj, then the curve ZT will be written as a linear combination of Sj times WJT. Then we will know the whole curve, right? Yes, and we are able to predict the curve after 120 days. So this is how we get this curve for the Montreal temperature data, okay? This dashed line here is the average temperature. Okay, so you can see here, when we do the LPCA, we actually assumed all the N curve coming from the same stochastic process with the same mean and the same covariant function, right? So in that case, in other words, we assume that these curves will have very similar trend, right? So the one reason that we are able to predict the Montreal data so well, because the Montreal data is very typical continental city weather, right? So you can see the prediction is very accurate. So if you think your data, your curves have different clusters, have different coming from different stochastic process, in that case, you have to be careful to do the prediction, right? Yes. So here, this is a kind of a little warning here. Okay, so here is the summary of the data. So basically here, I show you, give you a short introduction about the PCA. The PCA is a very important dimensional reduction tools for the multidimensional statistics, right? So you can see that function PCA is very similar to PCA, but function PCA is focused on the functions, right? And it can explore the variations among curves, and it can find the key features in the curves, and it can project the infinite dimension curve to low dimensional feature space. Okay, so this is the summary about the functional PCA. Any questions? Okay, so it's already 40 minutes. Let's have a 10 minutes break, and then I will show you the LPCA code, how to do LPCA in R. Okay. So I will stop my video and we will have a 10 minutes break.